In this video, we're going to continue to look at anti-differentiation. So in the previous video, Introduction to Anti-Differentiation, we talked about what actually it is and how to set it up. However, in this video, we're going to be looking at the properties of integrals and calculating the antiderivative of functions that are a bit more complicated. So if you're not familiar with anti-differentiation or differentiation, go back and look at the previous videos and then make sure you're comfortable with the concepts. So again, we'll look at the properties of the integrals. So first, when I'm talking about the integrals, that's this bit here. That's like the notation for you're finding the antiderivative. It's like when you had dx, when you're finding the derivative. However, for the antidiff, it's like this. You have the integral here and then dx with respect to x. So properties of integrals. So if we had the standard fx dx here, so that's just finding the antiderivative. So if it was x to the squared, it would equal x cubed 1 over 3, because then you bring the 3 down, the 3 over 3 is 1, and the 3 minus 1 goes to 2. So you have 1 over 3 x cubed. So if you have the integral of fx plus gx dx, this is equal to the integral of fx dx plus the integral of gx with respect to x. So this is similar to differentiation, when you could, if you had fx plus gx, then you could, if you wanted to find dx of the entire thing, then you could split this up into f dash x plus g dash x. And so the same thing applies with the antidiff. If you have the integral fx plus gx, you can split it up like this, which is very useful when you have two functions that you do know how to antidiff. However, added together, you can't add them together, and then you're left with an equation which you couldn't otherwise antidiff. So you can split it up like that. Also, if there's a constant, you can take the constant out. So if we had k times fx dx, this is equal to k times the integral of fx dx. So not getting rid of the k, so the k is still there in both instances. However, we've just taken the k outside of the integral. The reason for this is when you antidiff something, then it's only changing the x values. Of course, the constants come down and different variables come down. However, with a constant, the constant will remain the same. So we can do a quick example. If we had the integral of 3x squared dx, then we can calculate that with 3 inside. So if we do that, we get 3 times 1 over 2 plus 1, x 2 plus 1. So that's x, not times. The times there. So this is equal to 3 on 3 times x over 3, which is equal to x cubed. So you can get that answer. However, if we take 3 out first, x squared dx, then we get 3 times 1 on 3 x to the 3. And then once we finish that, we times them together, and we get the same answer. So that's just showing that you can take a constant out, which is useful when you've got lots of different terms, especially if there's a term on top, you can just quickly take it out as a constant, and then you can see that fx may look like a function that you've seen before. So now going to integration. So how do we antidiff ax plus b? And then this is to the power of n. So we've looked at in the previous video how to antidiff functions such like x squared. However, this time we want to know how to end up being able to antidiff something like 2x plus 3 to the power of 4 dx. So the first thing is just to write down the formula. We have ax plus b to the power of n, and this is equal to ax plus b n plus 1 over a n plus 1 plus c. So if you look at the different features of it, firstly it's going from n to n plus 1, but the middle bit is remaining constant. Then it's divided by a, and also divided by n plus 1. However, in general, what we've done here is, if you remember the chain rule, this relates to the chain rule. So if you have ax plus b, then you can find the derivative of that. So the derivative of the inside of this is a. So then you divide by a. And then you also have to divide by n plus 1. So the new integral. And we had to do that. If we're doing this, we could get x cubed over 3. So we had to divide by 3 divided by the power. And so dividing by the power we had to do before. However, the only new bit is really we have to divide by this a, and that is the diff of this. So before, when we use a chain rule, we let u equal something, and then we times, so let u equal something, then we times by du dx. However, now it's 1 over du dx, so we're putting 1 over a. So ax plus b, so this can, if you use this method, you can actually solve other things which are more complicated than ax plus b, but are within inside this bracket, such as things like 3x cubed plus 4 to the power of 5. So what we do here is we say that we have gx to the power of n. So whatever gx is, whatever type of function, dx with respect to x. And this is equal to gx to the power of n plus 1 divided by n plus 1. So that's just dividing by the new power. But the new bit is timesing it by the derivative of gx. So whatever the function derivative is here. So before with ax plus b, if you divide diffed ax plus b, we got a. However, gx could be any different function, so the derivative could be different. Once again, don't forget the plus c at the end. So we'll look at an example for this. If we had to find the antidiff of 2x plus 3 to the power of 4 dx. So you can think about this as 2x plus 3. So you can imagine that as x. So you're replacing all a different variable. So you have 2x plus 3, and then we've increased 4 to 5. We have to divide by the new variable 5. Most importantly, we have to times by this, the derivative of 2x plus 3, which is 2. So this is equal to 2x, I should write the plus c at every step. This is equal to 2x plus 3 to the power of 5 over 10 plus c. Now when we did calculate that, there was an exception that n cannot equal negative 1. And the reason for this is we have n equals negative 1, and then we plus 1, negative 1 plus 1 gives us 0. So there's a special case when n equals negative 1. So if you remember with log, if we had log ex, and we wanted to find the diff of log ex, this is equal to 1 over x, which is also representative as x to the negative 1. So then when we want to anti-diff something that's 1 over x, we're going to get the log function. So a similar thing before with the ax plus b, we can do the same thing, but we just have to worry about this a, and we have to divide by whatever the diff is here. So if it was a integral of 1 over x dx, this is just equal to log e modulus x. So quick thing, why is there a modulus there? That's because x has to be greater than 0 for log values. However, when you have just 1 over x, x can be any real number. So you have to put the modulus value there to make it so that x can also be less than 0 as well, all real numbers apart from 0, because 1 over 0 is undefined. So that's why I had the modulus there. However, if they had find the integral of 1 over x with a restriction on x, then the modulus may not be necessary. So we have that 1 over x is equal to log e modulus x. But what about if we want to integrate with respect to ax plus b, or to a different function? So we can do it for a general function. We'll call that general function gx. So here we want to know what gx to the power of negative 1 dx is equal to. Remember, this is just equal to the integral of 1 over gx dx. So this is equal to 1 over g dash x times log e modulus gx, goes modulus, plus c. So whatever the modulus is, whatever the function is, you find the derivative, go 1 over that derivative, and then times it by log e, the gx remains the same, and it goes inside here. And you can check that by diffing this. When you diff this here, you can let u equal gx. Then when you diff it, you times. So if we let u equal gx, then we have to times by du dx. So that means these two would cancel, and we would be left with the log e. We would be left with the 1 over gx. This is what we started with. Because we times by this du dx, we have to have the 1 over the diff to cancel these out, or to counter the fact that we have to times it when we diff it. But the main thing is, if that's complicating you, just remember that when we diff, we times by du dx or times by g dash x, but when we anti-diff, it's 1 over that value here. So doing a question, we have 9 over negative 2x plus 3. So first thing you can do is remember the properties integrals that we did at the start of the video. So this is equal to 9 integral 1 over negative 2x plus 3 dx. So we can take the constant out. This is equal to 9 times 1 over negative 2. So the negative 2 comes from d dx of negative 2x plus 3, which is equal to negative 2. Times that by log e modulus negative 2x plus 3 plus c. So final answer is negative 9 over 2 log e modulus negative 2x plus 3 plus c. And then if there was a restriction on x, we wouldn't need the modulus.